In 2003, Leonard Susskind published a paper that set the physics world on fire. String theory, the elegant theory of everything, that was supposed to explain our universe with mathematical perfection, doesn't give you one universe. It gives you 500 universes, a number so absurdly large that if you wrote it out it would have 500 zeros. Some physicists called it the death of string theory. Susskind called it the landscape, and the debate that followed nearly tore the field apart. This is the story of the most controversial idea in modern physics. To understand why this matters, you need to know what string theorists were searching for. Since the 1980s, string theory had been sold as the ultimate answer, a single mathematical framework that would unify gravity with quantum mechanics, explain every particle, every force, every constant in nature, one theory, one set of equations, one universe. The idea was beautiful. In string theory, the fundamental building blocks aren't point particles. They're tiny vibrating strings. Different vibration patterns create different particles. An electron is one vibration. A quark is another. Gravity itself emerges from the strings, but there was a problem. String theory requires extra dimensions beyond the four we experience, time plus 3 spatial dimensions. Depending on which version you're working with, you need anywhere from 10 to 11 total dimensions. The extra dimensions have to be curled up, compactified, into shapes too small to see. And here's where things get weird. There isn't just any way to curl up those extra dimensions. There are many ways. Imagine a piece of paper. You can roll it into a cylinder. You can fold it into origami. You can crumple it into a ball. Each configuration is different, and in string theory, each configuration gives you a different universe with different physical laws. For decades, string theorists assumed there would be some deep principle, some beautiful mathematical reason that would single out any configuration. The true vacuum, the real universe, our universe. Leonard Susskind was about to show them they were wrong, catastrophically wrong. By the early 2000s, Susskind had spent over 3 decades working on string theory. He'd co-discovered the theory itself back in 1970. He'd fought a 28-year battle with Stephen Hawking over black hole information. He'd helped develop the holographic principle, the idea that reality might be a projection from a lower dimensional surface. But in 2003, he was working on something that would become far more controversial than any of that. String compactifications. Think of it like this. You have a 6-dimensional space, the extra dimensions that need to be hidden. To compactify them, you wrap them up into a geometric shape called a calabi-yau manifold. These are incredibly complex, beautiful mathematical structures. They look like abstract sculptures, twisted, folded, multi-dimensional origami. Each calabi-yau manifold is different, and each one gives you different physics. Change the shape, and you change the masses of particles. You change the strengths of forces. You change the cosmological constant, the energy of empty space itself. You get a different universe. So the question became, how many calabi-yau manifolds are there? In the 1980s, physicists estimated maybe a few dozen. By the 1990s, the count was in the thousands. Uncomfortable, but manageable. Surely there would be some principle that ruled out most of them. Susskind started doing the math properly. He wasn't just counting calabi-yau shapes. He was counting ALL, the possible ways to configure a string theory vacuum, different manifolds. Different ways to wrap brains around cycles in those manifolds. Different values of flux. Essentially, different magnetic field configurations threading through the extra dimensions. The number kept growing. Thousands became millions. Millions became billions. Billions became something unthinkable. 10,500 typo. That's 1 followed by 500 zeros. To put that in perspective, there are about 1080 atoms in the observable universe. The number of possible string theory vacua is larger than the number of atoms in a trillion universes. And here's the devastating part: there's no principle that picks one over the others. Every single one of those 500 configurations is a mathematically valid solution to string theory. Each one is a possible universe. Each one has different physical laws, different particle masses, different force strengths, different values for the fundamental constants. Most of them are completely inhospitable to life. In most of them, atoms can't form, stars can't ignite, chemistry doesn't work. The universe either collapses immediately or expands so fast that nothing can ever clump together. But somewhere in that vast landscape of possibilities, Susskind's term for this space of universes, there are configurations where the constants are JUST, right, for complexity, for planets, for life. And we happen to live in one of them. Not because string theory predicted it, but because if we didn't live in one of the rare life-permitting universes, we wouldn't exist to ask why. This is called the anthropic principle. And most physicists hated it. Susskind was sitting in his Stanford office, staring at the numbers, when the full implication hit him. String theory wasn't going to predict the mass of the electron. It wasn't going to calculate the strength of gravity. It wasn't going to explain why the cosmological constant has the value it does, because for every universe where the electron has one mass, there's another universe where it has a different mass. For every universe with our strength of gravity, there's another with gravity 1,000,000,000,000 times stronger or weaker. String theory gives you a landscape of 500 possibilities, and we're in one of them not because it's special, but because it's one of the rare ones where we can exist. As Susskind would later write in his 2005 book, The Cosmic Landscape, this was like asking why Earth is the perfect distance from the sun for liquid water. Not because the laws of physics required Earth to be in the habitable zone, but because if it weren't, we wouldn't be here asking the question. The elegant dream of string theory, one theory predicting everything, was dead. But Susskind didn't see this as defeat. He saw it as reality. Think about it this way. Imagine you're trying to explain why a river flows through a particular valley. You could search for some deep principle that uniquely determines Tiat Valley and no other. Or you could recognize that rivers flow through lots of valleys, and you happen to be standing in one of them. The river didn't choose your valley for some profound reason. It's just that valleys exist, water flows downhill, and here you are. The landscape was like that. String theory creates a vast space of possible universes. Most are empty and boring. Some have stars, fewer have chemistry. Even fewer have the delicate balance needed for complexity in life. We're in one of the rare ones. Not special, just lucky. Susskind started working through the mathematics. He focused especially on the cosmological constant, the energy density of empty space that causes the universe to accelerate in its expansion. This was a major puzzle in physics. Quantum field theory predicts the cosmological constant should be Huji, about 120 times larger than what we observe. That discrepancy is the worst prediction in the history of science. Our measured value is absurdly, impossibly small, unless there are 500 different universes with 500 different values of the cosmological constant, and we're in one of the rare ones where it's small enough for galaxies to form. In most universes, the cosmological constant is too large. Space expands so violently that matter can never clump together. No stars, no planets, no observers. In our universe, it's incredibly tiny, but not zero, just small enough for structure to form. The anthropic landscape explained this. Not through some elegant mathematical principle, but through sheer statistics. With 500 tries, some universe is going to get the value right by chance. Susskind called this the anthropic landscape of string theory. And when he published the Zordo 30219, posted to the arXiv in February 2003, the physics community exploded. The landscape idea split the string theory community down the middle. Some physicists saw it as honest. String theory was revealing its true nature. not a unique theory of everything, but a vast framework with countless possibilities. The anthropic principle wasn't pretty, but if the math led you there, you had to follow. Others saw it as surrender. The loudest critic was Lee Smolin, a physicist at the Perimeter Institute in Canada. Smolin had been skeptical of string theory for years, but the landscape was the last straw. In 2006, he published The Trouble with Physics, an entire book arguing that string theory had become unfalsifiable pseudoscience. Smolin's argument was simple: if string theory predicts 500 different universes and you can't test which one is correct, it's not physics anymore, it's metaphysics. You're explaining our universe by saying, well, some universe had to have these properties and we're in it. That's not a prediction, that's not science. Susskind fired back. He argued that the anthropic principle is used all over science. We explain Earth's orbit by noting that planets form at many distances from their stars, and we're on one where liquid water exists. We explain the sun's properties by noting that stars come in many sizes, and we orbit one that's stable for billions of years. Why is anthropic reasoning legitimate in astronomy but forbidden in fundamental physics? The debates got heated. Smolin and Susskind appeared together at conferences. They published responses to each other's papers. Smolin called the landscape the end of science. Susskind called Smolin's objections wishful thinking. As Susskind described the disagreement, the string theory community had been searching for a unique vacuum, the one true configuration. But nature doesn't care about human aesthetic preferences. If the math gives you 500 solutions, you can't wish them away just because you don't like the implications. But the criticism went beyond Smolin. Some string theorists felt betrayed. They'd spent decades working on this theory precisely because it promised unique predictions. Now Susskind was telling them that uniqueness was never on the table. Others worried about the future of the field. If you can't predict the electron's mass, if you can only say, in some universe it has this value, what's left to calculate? What problems can you solve? And there was a deeper philosophical unease. The landscape implied something truly strange, that our universe isn't alone. Those other 500 configurations aren't just mathematical possibilities. They might be real, actual universes existing somewhere, somehow, in what became known as the multiverse. You can't travel to them. You can't observe them. But if string theory is right, they're out there. Universes where the electron is heavier, gravity is weaker, atoms don't form, vast cosmic wastelands. And we're in one of the rare fertile islands. To this day, the debate hasn't been resolved. Susskind published The Cosmic Landscape in 2005, a popular science book defending the anthropic principle in the multiverse. Smolin continues to argue that string theory lost its way. New generations of physicists enter the field and have to choose: is the landscape a feature or a bug? Here's what the landscape changed forever. First, the nature of string theory itself. Before 2003, string theory was sold as a potential theory of everything, capital T, capital E, one framework that uniquely determines all of physics. After Susskind's landscape paper, that narrative collapsed. String theory is now understood as a framework that contains many possible theories, a meta-theory if you will. Some physicists embraced this. Others abandoned the field. Second, the role of the anthropic principle. For decades, using anthropic reasoning in physics was seen as giving up, admitting you couldn't find a real explanation. The landscape made anthropic arguments unavoidable. If there truly are 500 universes with different properties, then of course we're in one of the rare life-permitting ones, not because we're special, but because otherwise we wouldn't be here to observe anything. Whether you like it or not, that's a legitimate explanation. Third, the multiverse became mainstream. Before Susskind's paper, the multiverse was mostly science fiction. After 2003, it became a serious scientific hypothesis. Not proven, probably never provable, but a natural consequence of string theory's mathematics. Susskind wasn't claiming we'd ever observe other universes. He was claiming that if string theory is the correct description of reality, those other universes are a mathematical necessity. And that changes how we think about why our universe has the properties it does. Today, in 2026, the landscape is still controversial. You can find string theorists who embrace it and string theorists who hate it. You can find physicists who think the anthropic principle is profound and physicists who think it's a cop-out. But what you can do is ignore it. Susskind's 2003 paper forced the entire field to confront an uncomfortable possibility, that the universe we observe isn't uniquely determined by elegant mathematics, that there's no deep principle explaining why the electron has the mass it does, or why the cosmological constant is so small. Maybe, just maybe, it's statistics, vast numbers, chance. We're the lottery winners who get to ask why we won. And Susskind has a connection here to his other great contribution, the holographic principle from 1994. If the universe is fundamentally holographic, with all information encoded on a distant boundary, then maybe the landscape is part of that encoding. Maybe different vacua correspond to different boundary conditions, different ways of projecting a three-dimensional universe from two-dimensional data. That's still speculative. But it shows how Susskind's ideas connect across decades, from strings to black holes to holography to the multiverse. Leonard Susskind is 86 years old now. He's published over 300 papers, won the Sakurai Prize, fought a 3-decade war with Stephen Hawking and won. He's trained generations of physicists at Stanford. He's written best-selling books explaining his ideas to the public. But the landscape might be his most lasting legacy. Not because it's beautiful, it's not. Not because it's satisfying, it leaves more questions than answers. But because it's honest. String theory gives you 500 universes. Susskind had the courage to say it out loud, even when the rest of the field wanted to pretend those other universes didn't exist. Some call it the death of physics. Susskind calls it reality. And reality doesn't care what we want it to be. The next time someone tells you that science is about finding the answer, the one true explanation for everything, remember the landscape. Remember that sometimes the universe is messier than we want it to be. That sometimes the answer is, we're here because if we weren't, we wouldn't be asking. It's not as elegant as a single equation that explains everything. But it might just be true. If you want to understand how Susskind's landscape connects to his other breakthrough, the holographic principle, and the idea that reality is a projection from a lower dimensional boundary, check out the next video. Because once you see how all these pieces fit together, you realize Susskind hasn't just been doing physics for 50 years. He's been rewriting reality itself.